Hello and welcome to this demo. Today we will be flattening this green cover using ExactFlat for Rhino. This cover came in as a collection of surface objects, so our first step is going to be to first join everything together and create a single poly surface. Although we want to flatten this as multiple pieces, we're not just going to flatten surface objects. We're first going to create a mesh from it and then use the adaptive remesh to condition our mesh before flattening. So we're going to join all these pieces together to form a single poly surface object, and then we're going to create one single mesh out of the poly surface object. The reason we do it this way is so we have very clean preserved edges between all the different surfaces. So if I were to select everything, we got 30 surfaces here. If I were to create a mesh out of this, and I'm just going to go ahead, simple controls, more polygons, we'll go ahead and click OK. If we start to examine this mesh, cell mesh, isolate. So we're going to hide all the surfaces. We're just looking at the meshes. If we look at the boundaries between these meshes, none of them line up. So none of these quads are lining up when we mesh this separately. So the reason we join everything together, so if we now, when we don't join it together, we don't have aligned boundaries, so we're going to join it together first, and now if we create a mesh, again I'm just going to use the more polygons and click OK. Now if we start examining the boundaries, cell mesh, we're going to isolate the mesh. When we start looking at the boundaries, everything lines up, so we've got much better mesh now, and this is going to greatly improve the reliability of ExactFlat sewing algorithms for when we create our new mesh using the adaptive remesh. ExactFlat's going to be able to recognize the boundaries, sew them together, and preserve those boundaries. So that's why we join everything together to create a single poly surface first before we create a mesh. So we're actually not going to keep this mesh here. There's a couple characteristics that I don't like about this mesh. So we're going to delete the mesh. We're going to use show to reveal the surfaces again, and we're going to use the Rhino mesh tool again, but instead of using simple controls, we're going to switch over to detailed controls. So this cover was modeled in millimeters, so as we move our mouse we can get a bit of an idea for the scale. So we're going to manually set our meshing tolerances here. So as a general rule, I always set the maximum aspect ratio to 2. That just means that our longest edge is going to be at most twice the length of our shortest edge on the quad or triangle. So this helps to control and minimize high aspect ratio triangles. So just kind of moving the mouse here, we're always going to start a little high. I'm going to set my maximum edge length to about 100 millimeters and my minimum edge length to 10 millimeters, and we're going to click preview. This is going to give us a bit of an idea for whether we need to increase these values or decrease these values. So I would like to see a few more triangles with quads along here before I use the adaptive remesher. So I'm actually going to change these. So I'm going to change it to 5 and 50. I'm going to cut them in half. And we'll do the preview, and we're hopefully going to be doubling our triangle and quad count here. So our mesh is looking a lot better now already, so we're going to click OK. Standard best practices is to always keep your different meshes and surfaces, any kind of work you do, on separate layers. So I'm going to create a new mesh layer here. I'm going to use the cell mesh command to select my meshes, and I'm going to change them to the mesh layer. Now what I can do is I can turn off my surfaces and only view the meshes. So we've created one single mesh from meshing one single poly surface. So our next step is to explode this mesh so we can actually rearrange the pieces into component pattern pieces. So before we started looking at this, I actually duplicated the boundaries of where we want our pattern pieces to go. So we can actually highlight them in red, and this makes it a little easier to select the pieces for creating our pattern. So we can see we've got our boundary right across the top here. So I'm going to start selecting my mesh here, and I'm going to join these together as one single pattern piece. And we're just going to repeat the process for all the pieces that form our pattern pieces here. Join those together, join these together. Join the right and left half of these together. And we're actually going to join all these together too. So this would be the windshield here. We can actually see where the cutouts are. And I actually identify these as a boundary that we want to keep. However, for flattening, it's much easier to actually fill these in And what we're going to do is we're going to use the ExactFlat trace command right here, and we're going to trace this boundary profile back onto the pattern piece after flattening. So for flattening purposes, we're going to join all of these together into one single sheet. And then lastly, we've got our pieces down here along the bottom. And we'll join these together as well. Now we'll just do cell mesh. We've got 7 pieces, which is what we should have. So we've got all our pieces joined together now. So when we created a mesh from the poly surface, what happened is it created individual meshes for every single surface, and then it just joined them all together, very much the same way we did here. And because we had independent collections of vertices and triangles, one independent collection per surface, when we use the explode command, the command actually goes out and searches for those collections, and it's going to break them out into separate meshes. So if I were to explode these, I would again explode them into 7 different meshes, or however many meshes we have here. And similarly, if ExactFlat were to try and flatten this, it would again explode them into the individual component pieces. So what we need to do is we need to eliminate all the duplicate vertices and merge all these independent collections of triangles and faces into a single collection. And the way we do this is with the Rhino weld command. So we're going to type in weld. We're going to select all of our meshes, and we're going to weld them all with an angular tolerance of 180 degrees. And what this is going to do is it's going to go through all our meshes, and it's going to find duplicate vertices, so 2 vertices within the same mesh container that occupy the exact same space and time, and it's going to merge them together into a single vertex. So now, if I select one of my pieces here and try to explode it, explode's not going to work because I've merged all the duplicate vertices. We only have one unique collection of vertices and triangles now, which is what we want. So before we flatten these, as we look at them, we can see we've got mostly quads, and most of the triangles are the same size. However, we do have some fairly high aspect ratio triangles, and we do have a lot of triangles that aren't really needed. So when we consider the back piece here, it's mostly flat. We have a lot of triangles or quads all the way down the back here. So what we're going to do before flattening is we're going to use ExactFlat's adaptive remesher to both decimate the mesh and to simplify the geometry of the mesh. So to do this, we're going to switch over to the Mesh Tools tab of the ExactFlat toolbar. And very first, we're going to validate the meshes first. We're going to make sure we don't have any geometry problems such as geometrically degenerate triangles or topologically degenerate triangles. So we're just going to very quickly use the mesh validator rectangle, select everything, and it's telling us that all our meshes are valid. If we did have a problem, that would have to be fixed before we can use the remesher, but we don't have any problems, so we're good to move on to the adaptive remesher. So we'll start the tool by clicking this icon here for the adaptive remesher, and again, we're going to rectangle select all our meshes. Once the dialog comes up, before we change any settings, we're always just going to click the Start button, and this is going to give us a baseline. It's going to let us preview the mesh to see what the quality is. And if we need more triangles, then we can reduce the tolerances here. If we need fewer triangles, we can increase the tolerances. So the way the tolerances work is they are the maximum allowed distance between, we've got surface and boundary tolerances. They're the maximum allowed distance between the original surface and the new surface created by the remesher. And it's the maximum allowed distance between the original boundary and the new boundary created by the adaptive remesher. So if we need to preserve more detail, create more triangles. In this case, we've gone from thousands of triangles or vertices down to simply a couple hundred. Then we need to reduce the allowed distance. So in this case, we're going to reduce our distance to 30 for all our values here. We'll click Start again, and we're going to see meshes that now have more vertices. So we're preserving more detail. So we can see we've got more triangles here, more geometry, and we're preserving more of this detail. If we reduce it even further, we'll do 10, 10, and 10. We're going to end up with even more triangles and vertices on our new mesh now. So we'll go ahead and we'll click OK to accept changes. So at this point, it's safe. We can start flattening now. So to flatten these objects, we're going to switch over to the Tools tab of the ExactFlat toolbar, and we're going to click the Flatten command to start the flattening process. So the flatten command is simply just one of our pre-flatteners. However, it is the entry point into the ExactFlat flattening process. So we always have to use the flattening command to start flattening things. So the flattening command is going to create the flattening workspace, as well as use our press pre-flattener to create an initial unoptimized flat pattern. So at this point, we're going to make our ExactFlat pattern layer the default layer, and we're going to turn off all the other layers because we don't need to see this information at this point. We're also going to minimize our perspective viewport by double-clicking on the title, and we're going to maximize our top-down viewport by double-clicking on the title here. So we've already used one pre-flattener when we used the flatten command. We used the press pre-flattener to create our initial unoptimized flat patterns. However, when we look at these patterns, we've got flipped triangles on this one here, and for most of the pattern pieces we see red, which indicates we have high strain. So all the colors on the pattern pieces all represent the relative amount of strain on the pattern piece. And if we consider the 3D reference model, we can turn this back on and examine it at any time. So I'm just going to switch back to our 3D perspective viewport. So we've always got a reference model and a 2D pattern, and the strain is always the same on the reference model as the 2D pattern. So we can see where our areas of high strain are on our pattern pieces. So if we consider our 3D model to be a rigid shell, the strain represents how much we're going to have to stretch and pull the 2D pattern pieces to get them to fit back onto the 3D model. So in this case, we have high strain on all of our pattern pieces, which needs to be dealt with. So really, the optimizer, the goal of the optimizer is to reduce the strain and average energy density to as close to 0. But because ExactFlat is a two-stage flattener, we have two different sets of tools for doing this. So we've got our pre-flatteners, which are the very first tools that are used, and our flatten tool does use one of the pre-flatteners to create the patterns. They're very, very fast tools, and their goal is first and foremost to remove flipped triangles. So when we look at this piece here, we can see we have flipped triangles here, and these are just triangles that are folded in under themselves to create a fold or a wrinkle. And the second goal of the pre-flatteners is to reduce the strain on the pattern piece and eliminate a lot of the red coloring. So we can do this with any of ExactFlat's pre-flatteners. So we've got our fracture pre-flattener, our pelt pre-flattener, and we've got our CCM pre-flattener. So for these pieces, I'm just going to start with fracture, and as I start selecting edges, we're going to get a different pattern piece for every single selection point. So the biggest goal here is just to remove flipped triangles and to reduce the strain as much as possible. So you don't have to spend a lot of time clicking around getting the absolute best pattern. So long as you don't have flipped triangles and you don't have a lot of strain, that's a good starting point. So again, we'll do this with this next piece. We've eliminated there weren't any flipped triangles, but we've expanded the piece and we've eliminated a lot of the strain. The same for over here, and because this piece is actually near developable, in this case we ended up with a pattern that is very, very close to the perfect pattern. So we'll just repeat the fracture process on the remainder of the pieces, and for this one down here, by fracturing it, we've eliminated the flipped triangles as well as reducing the strain. We still do have quite a bit of strain in this area here, but because of the nature of this piece, it's a very thin piece. This is probably more of a local anomaly than anything, so we're not going to worry about it. The optimizers will succeed in removing the strain. So we'll just fracture the remaining pieces here, and now we're good to go. So by using the fracture algorithm, we've spent very, very little time, and we now have pattern pieces that are very close to final pattern pieces. So we've greatly reduced the amount of time that's going to be required for the optimizer to optimize these to the final pattern. So now we're going to go ahead, we're going to optimize the pieces. So we're going to select all our pieces here, and we're going to go ahead and press enter on our keyboard. So at this point, we are now looking at the spring settings. So we're going to leave all of our settings at defaults. And we're going to use a simple cotton for optimizing this pattern. If we do need to use a different material, we can click the Browse button to open up the ExactFlat material browser, and we can select from one of ExactFlat's 85 default materials. If there isn't a material in the library that works or suits your needs, then we do have the ability to add custom materials to the database. You can either measure the mechanical properties of the material yourself, or we do partner up with a university, and for the cost of about $25 US, it usually takes about 5 business days. They will be able to measure the mechanical properties of your material for them. I believe you only need to send about a 1 foot by 1 foot swatch of material, and once they're done measuring the properties, they will send you back a report which you can then use to create your own mathematical model of that material in ExactFlat for your private use. So once we select our material, we just click OK, and now we're going to start the optimization process by clicking the OK button. So as ExactFlat optimizes the pattern pieces, we're going to see not so much with this pattern because we're very, very close to optimal pattern pieces already, but we're going to, for these two pieces down here especially, we're going to see the shape is going to change and the colors are all going to change more towards white. So as I've already mentioned, the colors on the pattern pieces do represent the amount of strain on the pattern piece. So the default ExactFlat legend has white representing 0 strain, cyan or blue is representing 5% strain, green is about 10% strain, yellow is 15%, and red is 20% or more. So as we optimize the pattern pieces, we're reducing the average energy density, or in the case of these pieces, we're actually expanding the pattern piece, we're adding material, and that's how we're reducing the average energy density. So because we're adding material, reducing the energy density, we're reducing the strain. So we can see this being reflected in the strain analysis by means of the colors all changing from red and yellow. They're all changing towards blue and mostly white. So a couple ways we know that the patterns are a good fit. The primary way is simply by looking at the color of the pattern piece. When we see the color changing towards white, we know we've got a very low energy density on the pattern piece, and we know that because we've got very low strain or energy density, that's going to be a good fit. A couple other ways we can tell that we have a good fit is by looking at the average energy density in the ExactFlat report. So the ExactFlat spring status is going to tell us what our average energy density, and for this piece, our average energy density is less than 1/10 of a Newton meter, which is very, very low. We can also see our single maximum or greatest amount of energy density on any point in the mesh is also under 1 Newton meter, which is extremely low. So these two metrics alone are telling us that we have a very, very good fit for the pattern in terms of energy. We're not going to have to stretch it very much to get it to fit on. Another way we can tell that we have a good fit is by comparing the perimeter length, and this is important when we're sewing our patterns together. We're always going to be sewing a left side to a right-hand side, so we want to make sure that the left and right-hand side are the same length. So we can compare the perimeter lengths of the patterns to make sure that we've got a good fit here. So a couple things to look for as far as the boundary length of the pattern piece. So for this piece here, our boundary length is about 5,500 millimeters. And we've also got our no seam stretch error. So I'm just going to switch back to piece 5 for this one here. So we've got 5,500 millimeters for the perimeter length, and our error is 26 millimeters. So what this error represents is when we compare the perimeter length of the 3D model piece and the perimeter length of the corresponding 2D pattern piece, the no seam stretch error is the difference between the two. So when we compare 3D to 2D, our perimeter length difference is about 26 millimeters. And when we consider that our error is 26 millimeters out of 5,500, that is a very, very small error. That's less than 1% error. So this is distributed around the entire perimeter. So when we go to sew this back together, just because of the stretch of the fabric, this error is going to be very, very manageable and not noticeable. So if this still is too much of an error, we do have some options that we can set in the spring settings, specifically the preserve boundaries option, and that's going to help to further reduce the no seam stretch error at the expense of adding additional strain to the pattern piece. We're going to go ahead, we're going to click OK, and now we're going to rearrange our pattern to make it a little easier to see where everything goes. So we're going to start with this piece here as the big long piece at the back, and what we're going to do is we're going to first rotate it. It looks like it's already in the correct orientation, but we're going to rotate it anyway. So we're going to use these 2 points as our reference, and I'm just going to hold Shift on the keyboard to snap my point along the horizontal x-axis, and we're going to rotate this so it's perfectly horizontal. Next, I'm going to use the ExactFlat Find tool to find all the neighboring pattern pieces, and the Find tool is going to allow us to rotate them and snap them back to where they should be. So we'll notice as I move my mouse along the edge here, we're seeing a highlight here, and if we look at the far right piece, we can also see a corresponding orange highlight. So that's telling me that those two edges match up. So if I click on this edge here, what's going to happen is the far right piece is going to rotate and move to match my selection point here. So using the ExactFlat Find tool, we can very quickly find and recreate our pattern. So when we look at the front windshield, we flatten this as a single piece, even though we do have cutouts for the windscreen. So to add these cutouts, we're going to use the ExactFlat Trace tool, and in order to do this, we need to go back to our 3D model. So we're going to turn on our 3D reference model, and we can see it down here to the right. And to make it easier, we're going to go back to our perspective viewport. So now we have our 3D reference model over here on the left, and we have our pattern over on the right. We also have our original layer with the boundary curves that we created, and on this layer we have 3 curves that were right on the surface, indicating the location of our windshield cutouts. So what we're going to do is we're going to trace these 3 curves onto this pattern piece, and we're going to do this using the trace command. So for all Rhino commands, including ExactFlat commands, the command line is always going to tell you what is expected of the command. So right now, after starting the trace command, it's telling us to select one or more object to trace. So we're going to select our curves here that represent the cutouts for the windshield. We're going to press enter when we're done selecting our curves. Next, it's telling us to select the ExactFlat model objects to trace onto. So this is our target for a trace. So we're going to choose our front windshield here, and we're going to press enter. This dialog appears when we're converting a curve or a spline into polylines, and this is just giving us a preview for how many vertices. So this is basically our fidelity for the trace curve. So if we move the slider all the way to the right, we're going to have a less fidelity or fewer vertices. If we drag it all the way to the left, we're going to have a lot more vertices. So we're just going to aim for something around 300 vertices or so is more than enough to do the trace. So we're going to go ahead and click OK. And ExactFlat is now tracing these curves onto the 2D pattern. So if we zoom out, we can see that ExactFlat has in fact traced them on. So to make this a little easier to see, we're going to switch over to the Highlights tab of the ExactFlat toolbar, and we're just going to turn off the edge highlight. So now that we've traced on our curves onto the pattern, we can go ahead and we can start adding notches to this pattern piece. So we're going to go back to our top viewport, and we're going to hide our model again by making the ExactFlat pattern the default layer. We're just going to turn off the pattern, and we're going to turn the model, and we're going to turn off the boundary curves. So now we're going to go ahead, we're going to use the ExactFlat notch tag tool. We're going to switch back to the Tools tab of the ExactFlat toolbar, and we're going to turn on the notch tag tool. So we're just going to use the default settings for the notch tag, and what this is going to do is it's going to create a simple slit notch. It's going to create it the entire length of the seam that we're adding, and our tag that we're going to create is just going to be a single auto-incrementing unique number, starting from 0 going all the way up to however many notches we add. So we're going to click the Add button. It's going to hide the dialog, and now we can start selecting locations on the edges here. So we'll notice as we select a point on one side, we're actually creating 2 notches. We're creating one on the left-hand side as well as the right-hand side of the seam. So this greatly assists with the sewing process. It allows us to ensure that the right and left-hand side are being sewn together at an even rate. So once we're done adding all our notches, we can go ahead and we can create a DXF, or we can just work with our pattern in Rhino. So once we've flattened the pattern pieces, you're not forced to use the ExactFlat patterning tools, although we do have patterning tools such as piece tags, notch tags, and our trace tools. You're not required to use them. You can simply just bring this pattern into another package such as Optitex or Gerber AccuMark. So the easiest way to do that is to create a DXF. And we can do this simply by clicking the DXF icon in the ExactFlat toolbar, and this is going to ask you to choose a location and a file name for creating a DXF. So we're just going to go to our demo folder here, the green cover, and we're just going to create this DXF called boat cover. So we've created our DXF, and now what we're going to do is I'm going to import this DXF into the document here, and we'll have a look at the file structure of the DXF. So I'm just going to use the import command, and we'll import our boat cover. And now we can see the DXF that we've created. So on our pieces here, our DXF is comprised of multiple layers. So if we can look at the layers over here, we've got a grain layer, cut layer, we've got our seam layer, notch tag, and we also have our traced lines layer. And this is because we traced the profile of the window cutouts onto this pattern piece as well. So we'll just drag one of these pieces over here, and actually I'm going to use the Rhino move command. I'm going to move this piece right from the point here, trying to get it on the interior point. There we go, and we're going to move it right here. That way it's perfectly aligned. So when we look at this piece here, we can see that our blue line represents the perimeter of the pattern piece. So this is our sew line. And we also have an optional or a red line here, which represents our cut line. So this is the sew line plus whatever seam allowance we have configured in the ExactFlat options. So if we look at our ExactFlat options real quick here, we'll expand the ExactFlat tab. We're going to go to the DXF export tree item. And when we look at our DXF seam allowance, it's set to 10 millimeters right now. So if we measure the distance between our seam line and our cut line, it should be 10 millimeters. So we'll just do the perpendicular, and we've got 10 millimeter difference here. So our blue line is our seam line, or the natural perimeter of the pattern piece. Our red line is our cut line, which is a seam line plus our seam allowance. And we also have a gray line here, which represents our grain line. So in this case, because we didn't manually specify a grain line using the ExactFlat grain line tool, the grain line is assumed to be the horizontal x-axis. So you can rotate your pieces however you need to before exporting a DXF, and you can safely assume that the horizontal x-axis is always going to be the grain direction. So one benefit of the DXF export is because we have so many layers here, when we import this into another system or even our cutting table, we can simply turn off the layers that are not needed. And in terms of a cutting table, we can assign different tools to different layers. So we might want to assign a pen tool to the seam layer. That way we're penning out where we need to sew to help with the sewing process. We may want to assign a wheel cutter to our cut layer to cut out all the perimeter. We may want to assign a drag knife to our notch layer to cut out the notches, and we may want to simply turn off our notch tag layer, or we could assign a pen tool or an airbrush to our notch tag layer to actually pen out the notches that are, or the tags that are created for the notches here. So this has been a demo showing how to flatten a marine cover. So to summarize, we started out with our surface, and once we had our surface, I'll just turn off everything else here. Once we had our surface, we went ahead, we joined our surface together into a single poly surface, and then we created a mesh from it. And the reason we do this is to ensure that all the boundaries between individual surfaces, when we create our mesh, we want to make sure all the boundaries are aligned in terms of mesh vertices. So we've created a mesh out of our surface, and we went ahead and remeshed it. Once we remeshed it, we flattened it using ExactFlat and created our pattern pieces. So once we had our pattern pieces, we used the ExactFlat pre-flatteners. Specifically for this one, we used the fracture pre-flattener to remove as much strain as possible. After we did that, we used the ExactFlat optimizer, that's the spring tool, to reduce the average energy density to as close to 0 as possible. We then used a combination of the Rhino rotate and move tools to move one of the pieces, and then we used the ExactFlat find tool to find all the neighboring pattern pieces and snap them back to the correct location. We then used the ExactFlat trace tool to trace the location of the window cutouts onto the pattern piece. And then we used the ExactFlat notch tag tool to create notch tags. Finally, we used the ExactFlat DXF export tool to create a DXF for the pattern piece. And that is the what we've imported into the document for comparison. So thank you very much for watching, and have a great day.